developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Today we are presenting our introduction to the AFRL Midwest Hub on the project for the development of a state-of-the-art coating for hypersonic leading edges. The Secretary of the Air Force, Frank Kendall, has outlined 7 new operational imperatives for the Air and Space Force to direct technical innovations. We are here to discuss operational imperative number 4, dealing with the tactical air dominance, namely for the 5th and 6th generation hypersonic vehicles and weaponry. Because of the advances in propulsion and design, these missiles and airframes can achieve speeds exceeding Mach 5.
Once these speeds are approached and surpassed, the airframe's structural integrity and stability must be maintained, especially the leading edges, which experience the most extreme environments imaginable. The leading edges of the hypersonic exceed temperatures of 2,000 degrees Celsius and heat fluxes over 1,000 watts per meter centimeter squared. The leading edge integrity must be maintained to ensure stealth, stability, and readiness of the airframe to fly.
Over the last 6 months of research, we have had tremendous progress. In this time, we have been able to develop multiple wet chemistry solutions to create a varying degree of viscosities for the coating application. The less viscous solutions allow for a very thin, highly crystalline coating to be applied. The highly viscous solutions, on the other hand, allow for application of the coating through a painting process and for a thicker coating with a more amorphous morphology. A variety of heat treatment experiments have also been explored to determine the temperature ranges available to convert the metal salt polymer solution to a metal oxide coating.
A variety of heating treatment experiments have been explored to determine the temperature ranges available to convert the metal salt polymer solution to the metal oxide coating. The solution is able to be heated to 1200 degrees C to fully ensure the full conversion of the polymer solution to a metal oxide coating. However, this conversion was also displayed at temperatures as low as 500 degrees C, which makes the process much more economical for large surface area coverage and for coating materials that cannot handle temperatures above 1000 degrees C.
Raman spectroscopy indicated that the coating applied had a definitive vibrational mode of the final metal oxide desired. This demonstrates that the coating is robust and thick enough to be identified via this spectroscopic technique and has some crystalline nature for the long-range vibrational modes of the crystal lattice. These Raman signatures were identified on all the substrates that were coated, including single crystal silicon, silicon carbide, glassy carbon, phenolic, carbon-carbon fiber weaves, and tungsten metal sheets. X-ray fluorescence imaging also allowed us to observe full range of the coverage of the coating on a 1-inch squared substrate. XRF analysis displayed a relative homogeneous coating of a metal oxide across the entirety of the substrate, indicating that this process has the potential to be utilized for covering very large surfaces like that of a large airframe. Cross-sectional cuts of the substrate were taken for SEM imaging to analyze the thickness of each coating applied and to observe the effect of successive coatings layered upon one another. It was observed that the coating adhered well to the substrate surface and stacked well with one another, creating an uninterrupted layer of metal oxide. More extensive SEM imaging is in the progress for us to provide some very nice and detailed images as part of this research.
Finally, we have been developing collaborations with other hypersonic testing groups to put our coatings through the rigors of equivalence to the environment experienced during hypersonic flight. We are looking for torch or laser testing to expose our coated substrates to temperatures approaching 2000 degrees C and heat fluxes of 500 watts per square centimeter. We will then extensively compare them to the uncoated substrates which experience the same exposure. This will give us a very good comparison of the robustness, oxidation, and thermal resistance of our coating system. Also, for the next phase of the project, we will have paired with Dr. Antar Elazab and his research group to do thermal modeling to see how our coating system will compare with uncoated and other coating systems.
Ideally, we will be able to observe how our coatings can handle the heat and stresses of hypersonic flight environments, both experimentally and theoretically, and develop detailed clues about the ultimate breakdown mechanisms of the high temperature coatings.